Without a crystalline structure, amorphous carbon is free and reactive. Ending dangling pi bonds with hydrogen can stabilize amorphous carbon compounds. Some short-range organization is discernible, as in other amorphous substances. TACI stands for tetrahedral amorphous carbon, which is also known as diamond-like carbon. Other common abbreviations for amorphous carbon are AC, H or HAC for hydrogenated amorphous carbon, and AC for general amorphous carbon. Amorphous carbon is the term used in mineralogy to describe coal, carbon generated from carbides, and other impure forms of carbon that are neither diamond or graphite. The materials are polycrystalline graphite or diamond materials in an amorphous carbon matrix, not really amorphous in a crystallographic sense. Significant amounts of other elements are also typically present in commercial carbon, and these elements can also form crystalline impurities. Creating fully amorphous carbon materials became feasible with the advent of contemporary thin-film growth and deposition methods in the second half of the 20th century, including cathodic arc deposition, sputter deposition, and chemical vapor deposition. In contrast to graphite's aromatic pi bonds, true amorphous carbon contains localized pi electrons, and allotropes of carbon cannot match the lengths and distances at which its bonds form. Additionally, it has a high concentration of dangling bonds, which result in differences in bond angle and interatomic spacing, as determined by diffraction, of over 5%. Depending on the settings utilized during deposition, amorphous carbon films have different characteristics. Characterizing amorphous carbon is mostly done by comparing the material's sp2 to sp3 hybridized bond ratio. Purely sp2 hybridized bonds make up graphite, while purely sp3 hybridized bonds make up diamond. Because of the tetrahedral shape created by sp3 hybridized bonds, materials with a high concentration of sp3 hybridized bonds are called tetrahedral amorphous carbon or diamond-like carbon, because of the similarities between many of their physical characteristics and those of diamond, as well as observable bond angle change. Experimentally, sp2 to sp3 ratios can be determined by comparing the relative intensities of various spectroscopic peaks, including EELS, XPS, and Raman spectroscopy, to those expected for graphite or diamond. In theoretical works, the sp2 to sp3 ratios are often obtained by counting the number of carbon atoms with 3 bonded neighbors versus those with 4 bonded neighbors. This technique requires deciding on a somewhat arbitrary metric for determining whether neighboring atoms are considered bonded or not, and is therefore merely used as an indication of the relative sp2-sp3 ratio. The sp2-sp3 ratio may appear to suggest a one-dimensional range of qualities between graphite and diamond when used to characterize amorphous carbon materials, but this is most definitely not the case. To further characterize and broaden the spectrum of properties provided by amorphous carbon materials, research is currently being conducted.